Okay, sure. Yes. So today I'm just going to give a brief introduction to the large models. So this is going to be a super condensed version of the NLP class you may be taking at the MIT or other schools. But because it's like a super high level overview, I'm not going to go into like much into details about like the exact instrumentation, algorithm, that kind of stuff. But if you are interested, feel free to ask questions at any time. Or if you are like interested in a particular topic, maybe you can give another lecture to give like a more in-depth introduction to that particular topic.
You minimize them.
Yes. Okay.
Bring it to the top.
Wait. Oh, okay. So before we get into the modern LMs, I'm just going to give a brief introduction to the recurrent neural network or RNNs. So this was a pretty popular model before the transformer was introduced. The initial idea is that we have a bunch of embeddings associated with like each word tokens. And on each step, we're feeding that embeddings into a RNN network, and we update the hidden states of that network. So essentially, you're feeding like each word token one by one, and after you feed in the whole sentence, you have a final like hidden states that should have like the information of all prior word tokens sequentially. And then you use the final hidden states to combine with a classifier to predict the most probable next word. So in this example, we have like a sentence like the student opened there, and after you feed in the whole like embedding, the classifier would output probability distribution that says maybe like the books is most probable next word in this sentence. So it has a couple of advantages. First, it can process any length input. So you have only like a fixed length hidden states. So no matter how long the input document is, the hidden states is of a fixed size. So that's good. And the second thing is that the model size doesn't increase for longer input context, which is essentially like but the disadvantage here is that the recurrent computation is slow. You have to process each word one by one. So the input processing time scales linearly as your like input sentence gets longer. And because we only compute the hidden states based on the prior hidden states, it's hard to access information from like many steps back. So if when you like come to like this point, it's very easy that for the model to forget about the information, maybe a couple of like sentence or a couple of words back in the input. So that's why we introduce transformer. So this figure was actually from like 3 slides ago. I just copied here. So the good thing about a transformer is that it has a global attention, that each word can interact with any other words in the input sentence or input document. So it treats like each word's reputation as a query to access and incorporate information from like other word tokens. The good thing about that is that like the number of unparallelizable operations doesn't increase with sequencing. So no matter how long your input sequence is, you can just use like one single operation to process all of them. And the second thing is that like the maximum interaction distance is of 1. So it's easier for the model to capture like long distance relationships between like the word in this sentence and the word in another sentence or so. But the transformer also have a lot of like drawbacks. And the one prominent drawback is that the time complexity is pretty high. So as you can see here, this was also from like a couple lectures before. We have like 2x here, which means that we're multiplying a matrix of the length of the input sentence by another matrix of the length of the input sentence. So that means that the time complexity of attention scales at n squared. This is pretty large when your like input document is pretty large. If you like feed in the whole document or maybe a whole like Wikipedia article into the model, the compute required is pretty large. And that's why there's a recent trend of like using linear attention. So the basic idea of linear attention is that we split the whole like very long input document into chunks, and we run attention within like each chunk, so that the sentence can interact with other words in the same chunk, and then we aggregate the information in a RNN style manner. So we essentially like combine the RNN with transformer to reduce the computation needed for attention. That's linear attention. Now I'm going to briefly talk about the pre-training LLMs. So LLM became very successful after we have like a pretty large scale pre-training. But how do people do the pre-training? So it's actually pretty simple. So suppose you have like an input document. You split the input document into overlapping windows, and you essentially feed the whole like input into the model and ask model to output to predict the new next token. So it's basically like next token prediction on the scale of like whole internet text. That's a pretty simple idea, right? But why is LLMs so successful? So, well, it's because that because we have like the whole internet text to train, the diverse data at like that much a larger scale is essential for the LLM to obtain this kind of capability. So if you think about the maybe the QA data set, one of the largest QA data set, which is called Squad 2.0, it has around like 50 million tokens. But the pre-training text data set we have right now, which is called like data comp LM, it has 250 trillion tokens, which is much larger scale than the largest QA data set. And if you count the whole like the internet text, it has around like 510 trillion tokens. That's like 10 million times larger than the largest QA data set we have. So within that like internet text, essentially you have some data on almost every like task you could think of. So that's why it has some good like multitask capability. It also has a lot of like diversity. So in the pre-training text, we have like web pages, code, and also like social media, like from Reddit, and all the papers, books, and Wikipedia articles.
David,
Yes.
why is 3,100 trillion total and only 510 trillion tokens indexed? Why are not the whole internet tokens all indexed?
Yeah, I feel like it's because a lot of the text are not like very reachable by the search engine. So the search engine indexes a certain amount of like web pages, but it doesn't cover the whole internet. if there's no like other web pages points to that web page.
Yeah, just want to add to that, right? So the index internet might be the intranet within the company or the government-owned data or the hospital data, right? Those are not available by the search engine on the internet, but those are the index internet.
Okay.
Yes.
So how much bigger is the dark web compared to dark web? Very deep web.
Yeah, I would say the dark one would be within the 100 trillion total estimation. So that's an estimation of the entire like internet, which includes the information outside of like search engine. Okay. So that's for like pre-training. Right now I'm just going to briefly introduce the types of like architectures we normally use for like language models. Essentially we have three main categories. One is the encoder-only model, second is the encoder-decoders model, and the last is the decoder-only model. So not going to go into like much detail about the exact difference between the architectures, but essentially the encoder models have like two-way attention. So if you're feeding like one word, it can attend to both like past tokens and future tokens. And on the other hand, the decoder models can only attend to past tokens. So if you have a like word in the middle of sentence, the decoder can only attend this word token to the first half of the sentence, but the encoder can attend to both sides, the second half and the first half of the sentence. And one famous like encoder-only model is called BERT. It's great for text analysis if you're doing any like sentiment analysis or like emotion analysis, that kind of stuff. BERT is usually a pretty good model to start with. And for the decoder-only model, I think almost all large language models right now are decoder-only. And I don't think there's any like modern models that uses encoder-decoder design right now.
Why? Why don't you think people use encoder decoders?
I think it's mainly about the performance. So I have a slide about like why people use. Actually, I don't have. Sorry. So the good part about like decoder only model is that I think we models like language completion more naturally. So if you want the model to generate like answer to a question, the generation process essentially it can only attend to the past tokens. It doesn't know the future token is generating. So the encoder architecture isn't that useful. And the second thing is that because we don't need to attend to like future tokens, the decoder only model is more like compute efficient. And I think that's the main concern in the LM training right now. So the most famous encoder-only model is called BERT. It was introduced in like 2018. It has 340 median parameters. And at that time, it was considered a pretty large model. But right now, because the large language model is getting increasingly larger, this is considered a pretty small model right now. And it was trained on books corpus and English Wikipedia, which amounts to around like 3,300 million tokens. But even like right now it's considered pretty much a small model. But pre-training the entire BERT on a single GPU is still pretty difficult. It was actually pre-trained with like 64 GPU chips for 4 days. So if like you want to train that on like one GPU, that would take around like 8 months, which is a lot of time. And the pre-training of encoder-only models is that we pre-train with mask token prediction. So essentially, like we mask a part of a sentence with a mask specialized like mask token, and we ask model to predict what is mask, like what is under this mask token. And in the original like training, they actually mask like 80% of the tokens, which is like a lot, and ask model to predict around like 15% of them. And the decoder only models are essentially like all the LMs we have right now. Starting with the GPT-1, which is 117 million models, million parameter models. And it gets larger pretty quickly. For like GPT-3, we already have like 175 billion models. And yeah, as I said before, like the good thing about the decoder-only models is that in models like language generation pretty like naturally. And if you want to pre-train a decoder-only model, you essentially ask the model to output the next most probable next tokens based on the past context. And after the introduction of the decoder like large language model, people find that this performance of the model scaled pretty predictably based on their like size and training compute. In like 2022, the Chinchilla paper, they introduced a 70 billion parameter model that was trained on like 1.4 trillion tokens. That was considered like a pretty standard and pretty popular scaling law paper. And a lot of people have followed that recipe of like 70 billion versus 1.4 trillion. That kind of like balance between model size and training tokens. But in the more like recent years, people have scaled like the training tokens more quickly than scaling the model itself. So the Llama 3 model, it has 3 billion parameters, but it was actually pre-trained on 15 trillion tokens. So this is like a 10% of the size as the Chinchilla paper, but like 10 times larger training tokens than that paper. So that's another also like pretty interesting trend we're seeing right now. Yes.
So we only saw the size of the training tokens, but we don't know the overlaps, right? Maybe the data quality is now high. What's the amount of new information is included in the training data?
Yeah, I guess that's also a pretty open question right now. Because of the scale of the text, we don't really know like how much overlap are there. And you still need to do a lot of like cleaning and duplication before you can use the training data set. And I think that's why people from which group, but from Stanford, they introduced a data set called like Red Pajama. That's actually a clean version of the DataComp LM data set, which includes like deduplications and cleaning of the data set. So essentially, like pre-training has been there for a long time. Like it was there in 2018 when the BERT model was released. But large language model is only getting popular after the ChatGPT was released in 2022. So what's the problem with like pre-training to prevent it from like being useful? Well, the most prominent problem is that in pre-training we're essentially like doing language modeling, we're predicting what's the most probable sentence that comes after the input sentence. But that doesn't equal to like assisting users. So in this example, we ask model to like explain the moon landing to a 6-year-old in a few sentences. And if you feed that into GPT-3, it will answer like explain the theory of gravity to a 6-year-old or explain the Big Bang theory to a 6-year-old, which has nothing to do with the answer to that question. So how do we fix this problem? Like we know that in the text document, these two sentences are like often like put together, but that's not the answer we want. And that's why people introduce instruction fine-tuning. In the instruction fine-tuning, we collect like examples of instruction and output pairs across like many tasks and fine-tune a large language model to that many tasks together. And the like instruction fine-tuning has become like very popular after we actually have a lot of data to fine-tune. So the supernatural instructions data set includes over like 1,600 tasks with like 3 million examples. That includes like all the tasks you could think of, including like translation, question answering, classification, sequence tagging. So almost all the tasks that you can do with like text alone. And this allows model to learn across like each task and achieve a better performance in each and like every task in the data set. And we also in our lab we actually have another like ongoing works that we collected a foundational like clinical multitask instruction tuning data set that includes like data from 13 clinical modalities and over like 5 million question answer pairs. We also show that if you train the model on like each task, on every task, it's better than if you only train the model on like a single task. And so how exactly do we optimize the model's response? And so that the model's response is like what we want? Well, that's when like people introduce preference tuning. So we're like optimizing the model's response for humans' preferences, which means like exactly how we want the model to respond to a given question. So here's the example. So this is a article taken from the Wikipedia, and for example, like we want to ask model to summarize a passage below, and the model will output maybe a good summarization and a bad summarization. So what we do is that we train a reward model that gives a reward to each of the summarization the model outputs. And we design the law so that the model is more likely to output the answer with a higher reward and less likely to output the answer with a lower reward. And that's actually what they did when they trained the GPT 3.5, the original ChatGPT model. So they essentially like they have 3 steps. First, they collect a bunch of like smaller scale so supervised fine-tuning data, question answer pairs, and train the model with like standard supervised fine-tuning on that like smaller scale data. And after that, they essentially have a larger set of questions and ask model to output multiple responses given the instruction, given the prompt. And they ask another set of labelers to rank the response from like best to worst. And then they train a reward model that takes this like human preference. And after they have this like reward model, they can scale up the training and train the model on like essentially all the topic with the reward model in hand. But one thing about like human preference is that they are noisy and uncalibrated. So for like one single like summarization, one person may give like a high reward, but another person may give like a lower reward. And maybe like some people just want to give like high reward to every response. So that would make the training process become kind of like noisy and harder to train. So that's why people will really introduce the relative preference tuning. So that's actually the state of the art algorithm right now. Like we ask model to rank the response in like best to worst, and they optimize the model based on the ranking instead of the numerical reward. And after training the model with like instruction preference fine-tuning, the model becomes much better at answering the question as compared to the original like pre-trained model. But reinforcement learning like preference fine-tuning doesn't always work as intended, because like human preferences are unreliable. For example, like if you ask the labeler to label your prompt and answer pairs, people will not like take half an hour looking at the whole response. That's not going to happen. So what people do is that they would take maybe like 5 seconds looking at the response. If it sounds like reasonable and good, yeah, they will give the model like a high reward. But that isn't always like correct. So sometimes like chatbots are rewarded to produce responses that seem like authoritative and helpful, but not correct. And that's actually one of the big problems in the like reward modeling and the RL training right now. And this can result in like making up facts and hallucinations. Like the model will make up facts however they can to prevent getting like a low reward. So that's what happens. And the second thing is that reward model doesn't always reflect like human preferences, and it may have like an unintended behavior. For example, in the this work, if you ask model like where are you from, and the model will give like a bunch of different answers, and the reward model will rank the answer higher if the model says like they are from a developed region, for example, United States, Canada, or Australia. But the model will get like a lower reward or like a penalty when they say they're from like Africa. So that's not what we want, right? Like we want the model to be fair and like treat like people from each region like equally. So that's some like unintended behavior of the reward model that we want to mitigate. Yes.
So there are papers that have demonstrated like a decrease in accuracy after like RLHF, or is that like a common known phenomenon that like the model performs worse after? With regards to hallucinations? I guess just in terms of like hallucinations, I'm guessing there must be some metric of like capability of the model to like reproduce facts. I wonder if like it gets worse after reinforcement learning. Yeah.
Yeah, I feel like it's a bit hard to compare because like before the preference tuning, the model doesn't answer your question. So
Oh, okay.
even when like it doesn't make up facts, it's not like very helpful and it's not very like comparable to the preference tuned model.
Okay. I just remember hearing somewhere like when it started to become like a very common thing to do to the models that people were complaining and saying, yeah, you train the models to behave more socially acceptable, but the models also become worse at like you know, accurately representing facts about the world, things like that. So I was just curious if there was like a cost there, but yeah.
Yes, I would say yes. And I think I've seen another like very recent work on like reasoning training. Like if you tune the model to doesn't output like malicious and harmful reasoning thoughts, the model will like hide their thoughts, but it will not change their own like behavior. So that's another interesting thing from the recent work. So it's pretty hard to do what they say like alignment in this sense to make the model both helpful and factual about like the question. So I'm going to introduce a couple of like more recent works on LMs. I would say like more recent works are more like focused on the efficiency of the training because like people have found that no matter how you alter the architecture, the model will behave like similarly after you train that on a very large scale of diverse text. So so nowadays, like people have found that the only improvement, well, not the only improvement, but the most improvement you will see that like after you make the model more efficient, and then you can train that on more data, which makes the model better with a given like fixed set of compute. So one thing, one very popular work in the efficient training is that it's efficient like low rank adaptation, which is called like LoRa. The motivation is that training the whole model takes a lot of compute and a lot of like GPU memory. So the solution they introduced is that they freeze the whole model, and then they train a small like adapter that updates the parameter in a low rank manner. So essentially they have two like matrices, which like compresses the embedding to a smaller size and then expand that back to the original size. So the combined parameter size of these two like adapters are pretty small. But after you expand that, you can like tune the whole model with this like smaller set of parameters. So if you don't have like a lot of like GPU memory, the LoRa tuning is usually still the best choice you can do, given you want to train like a large language model. And another popular thing is the mixture of experts. So you might have heard of this like model before, and essentially the motivation of this like mixture of experts is not like you have a couple of like models that specialize in each domain. In fact, like in most of the modern LM training, LM like mixture of expert models, the experts are not very interpretable. Like a given expert doesn't you cannot say like this expert is for like classification, that is for translation. We cannot we don't observe this kind of things. But what we do observe is that with the mixture of experts, we can train a much larger model given us much smaller compute. So what we do is that we have like multiple parallel networks simultaneously, like in like one layer. And during the full path of like each token, there's a layer that selects like which experts does token should go to. And because like for each token, it's only going through like a certain subset of the network. You save both like compute and GPU memory. And one very popular example is the recent like DeepSeek-R1 model. This is a mixture of expert model that have like 600 billion parameters in total. But for each token, only 37 billion parameters are activated. So essentially, you will save like 95% of the compute with this design. And another thing is called like quantization. So after you train the model, if you want to deploy the model on like a smaller device like phone, very like good technique you can do is that you can quantize the model to a lower bits. So before like during the training, the model are either trained on like 15 bits or 32 bits. But people have found that with a good like quantization algorithm, you can compress the model into maybe like 4 bits without losing any like noticeable performance. And not sure if I need to go to detail about this, but yeah, so the essential idea is that first you do some kind of like range clipping. So given a set of like weights, you first remove the outlier, you clip the outlier to a given like range, and then you scale the weights to the weights to the range of the given like target bits. For example, you are compressing the 32 bits to a int8 model. Then you will be like compressing the range of the weights to -128 to 127. But you don't have to scale like the zero weights to the zero weights in int8 case. So what you do is that you can actually scale and you can shift the weights to a given like to another like centroid. If you have more weights in the negative range, you can move the center point to the left, which gives you more accuracy given like a fixed range. And then you convert the model to a lower base and you do some kind of calibration to remove the quantization error you introduce in the quantization process. That's essentially the idea. But how? Yes.
Where's the quantization applied? At which stages? Like everywhere where you have, let's say, floating point values in the, I don't know, the intermediary layers, or I don't know.
Yes. Also, the quantization applies to every weight in the model. It doesn't apply to activations, and it doesn't apply to the last layer, which is the softmax classifier in the model.
So but because of the different, I guess, ranges, because across, I guess, the weights in the network, you will have like basically a library of those quantization, I guess, code books or something similar, or?
Yes. If you're interested, you can search for GGUF. That's a quantization library that's really popular right now. So with that format, you can actually find the quantized variant of each like popular large language models on Hugging Face right now. Yeah. but how far can we go? There was a recent paper that actually quantized the weights of the model to ternary weights, which are like either 1, 0, or -1. And they show that the model quantized to like 1.58 base have essentially like very similar performance as the original model. But to make this model with actually like 1.58 base, you actually need a new hardware. So the current like GPU hardware is not able to handle like this small quantization efficiently. So lastly, I think I'm going to introduce some like practical tips on like how to instruction fine-tune LLMs, because like I think this course is more like practical oriented. So, and I think most of you are maybe a lot of you are doing like LLM fine-tuning for the course project. So essentially we have like 4 steps. First, we want to prepare the data. We want to like convert the data to a conversation format so that it's easier to be handled by the like instruction fine-tune framework. And second, we need to choose a good starting point, and then we can like fine-tune the model before we send the model for like evaluation and deployment. So for data preparation, maybe we need to convert any data you have to a question answer format. So there are a lot of formats in like different data sets. Most of the instruction fine-tuning framework supports a lot of like different formats. So you just need to choose one. In this example, we have a question and answer in this like dictionary format, which has a problem and answer key and images and the list of images here. So we'll release the slides here. So if you can check like this thing, you'll see the list of formats you can use for your like LM fine-tuning. And then secondly, you want to start with a good starting point. That essentially means you don't want to use a very old model to fine-tune. Especially like you don't want to use the Llama 1, the original Llama model. That was actually a pretty bad model, even when it's released. And you want to start with smaller models first, but not too small. People have found that if you go anywhere like smaller than 3 billion parameters, the performance will decrease like pretty quickly, and you will not notice, and you will not see the performance even after like you fine-tune the model. So start with something that's at least like 3 billion parameters. And here are a list of like recommended models you can use as a good like starting point. For pure text tag, you can use a Gamma 3 and 20.5. You have like a very large cluster. You can also try the DeepSeek R1. For the text generation test, you can use 20.5 AL. It has a range from like 7B to 72B, which is pretty good for every like use cases. And then you can start like training the LLMs. They have like you don't want to use the raw like transformer package to train the model. You want to use an efficient LLM training framework, and will get like the training much faster as compared to just use the raw like Python script. And I have a few recommendations here. The Vero and the Llama Factory are the ones we use in our research. And the EVR one is a recent repo that's introduced by the same group as the Llama Factory. And I think they use VLM, which is a much more like efficient inference framework than the original like Llama Factories. And then you want to choose a method of training. I don't really have a lot of like recommendations here. You can either do like normal supervised fine tuning, or you can also do like RL, like preference tuning with like PPO, DRPO, that kind of stuff. I would suggest you to try like all of them and see what performs the best. The DRPO is a very like new thing, but it also has a lot of like issues with the algorithm. So it may not perform the best. So that's something you need to try. And depending on the size of the GPU you have, you want to decide if you want to use LoRa or you want to train the full model. And if you are dealing with like multi-model LMs, you want to decide like if you want to freeze the vision encoder or the projection layer that connects the vision encoder and the LM. Finally, you can train. And lastly, I just want to introduce two maybe like possible future directions in training and understanding like large language models. One popular trend right now is that how we teach large language model to reason. The most recent like DeepSeek R1 paper is a very popular work in this area. And I think a lot of the groups right now, I know are like trying to tune the model for like reasoning, for like fine-grained reasoning in all kinds of tasks. And the second very popular area is multimodal LLMs. We have a lot of like vision language models that are like public, but we don't really have any like audio or time series LLMs. And I think that's something people can work on right now. But that's it. If you have any questions, feel free to ask right now.
Great, thanks, David. Any questions, David? All right, if not, make sure you all submit your midterm reports today and be ready for our presentation on Thursday. Thanks, everyone.